Hey, fellow mathers! Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over 6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians! You're listening to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And you found a place where math is not about memorizing or mimicking, waiting to be told or shown what to do, but it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor mathematicians as we co-create meaning together. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be.
So if you haven't been tuning in lately, you've missed that we're talking about decimals and decimal multiplication.
Dun,
We
dun,
answered some
dun.
questions about how to help students make sense of decimals, and we're kind of things we think are not quite as helpful. In this episode, we are going to dive into a subtle and important facet of decimal multiplication.
So a few episodes ago, in fact, I believe it was episode 106, so 106. In episode 106, we talked about a subtle but important shift that we want to encourage students to make in whole number multiplication. Mm-hmm. And that subtle and important shift that we want students to make in whole number multiplication is that if students are really understanding multiplication, like say something like 40 times 17, kids will often start by finding 10 times 17 and 20 times 17 and then doubling that to get 40 times 17. So they sort of find the 10 times. Oh, that's a very handy, helpful thing. We want to do that. We want to encourage students to do that at first and then kind of scale up until they get to the number they were looking for, like 40 times 17. But then we want to make this important but subtle shift where we want to nudge kids to think about problems like 40 times 17 rather as 4 times 17 and then scale times 10. Mm-hmm. So if that's new to you, go back and listen to episode 106. It's really important. We do a lot of work with it and we get kind of in detail on it. But it's important to realize that we kind of have this strategy of scaling times 10 and then multiplying up, doubling up, multiplying up, adding things together until we get to the number we're looking for. That's kind of strategy one. Or the more sophisticated strategy where we kind of have this anticipatory thinking. We can look ahead and we realize since we need 40, we can find 4 times that thing and then scale times 10. And we end up then with a bigger number times 10 at the end versus in that first strategy, we're dealing with bigger numbers all the way along. Now, we want both, y'all. We need to have both happening in students. You might be like, Pam, I don't want to deal with those big numbers. I'd rather just deal with the small ones, which is kind of what the algorithm does. The algorithm only ever has you deal with digits. But we need kids to deal with those bigger numbers for a while because that's what helps them develop place value. That's what helps them develop a sense of magnitude and of what's actually happening. Don't get discouraged at that point if that takes them a little while to do all that thinking and reasoning because they're building their brains to really think multiplicatively. Then make the shift to get more efficient and sophisticated, not the algorithm, but to where they are thinking more about sort of anticipatory thinking. If I'm trying to find 40 times 17, I'm going to find 4 times 17. That's a smaller number to deal with. And then whoop, Now I can just scale that times 10. Bam! And I end up with the magnitude of the number that I need in the end, but I wasn't dealing with that big number until the very end. So that can be kind of helpful. How does that relate to decimal multiplication? I know Kim's thinking right now. She's like, Pam, this is supposed to be about decimal multiplication. Okay. So what if we had a problem like 0.4 times 17? Well, if you listen to last week's episode where we really helped you think about and help students think about problem strings that could help them really deal with what it means to think about times 0.1 or times 1/10. We want to do that first. So if we have that going and we have students thinking about 0.4 times 17, then they might think, well, can I think about 0.1 times 17, a tenth of 17? Now, again, we have to do some work there so that this makes sense to students. They have a feel for it, but we're sort of dividing by 10. So if I think about 1/17, then to get to 1, I divide by 10. So divide 17 by 10, and we're dealing with a tenth of 17 being 1.4. Or help me, 1.7. Sorry. So a tenth of 17 is 1.7. Now, again, that beginning, the kid that's kind of getting a feel for this might then say to themselves, well, if I've got 0.1 times 17, but I need 0.4 times 17, then maybe I'll double that to get 0.2 times 17. So that would be 3.4. And then maybe I'll add those together to get 0.3 times 17. Or maybe I'll double the 0.2 times 17 to get the 0.4 times 17. So if I'm going to double 3.4, that's 6.8. And now I've been able to think about 0.4 times 17 kind of in chunks that I understand. I understand a tenth of a number, and now I can just sort of scale that up until I kind of get to where I'm going, scale out that tenth to 4/10. And that would be a fine way for students to start solving some multiplication with decimal problems. But then, just like we made the shift with whole numbers, we want to make the similar shift with decimal numbers. So when I see 0.4 times 17, if I can sort of step outside the problem and think using anticipatory thinking, kind of plan my attack, then I might recognize that I could do 4 times 17 and get that 68, and then scale times 1/10. So now I've got 4 times 17 is 68, and then times 1/10 is now that 6.8.
Mm-hmm.
So to say that one other way, I can either think about 0.4 times 17, and I'm really writing, I just wrote it down. I wrote 0.4 times 17. I can think about that as 0.1 times 17 times 4. And I might do that times 4 by doubling and then doubling again. I might just know, well, probably not in this case, but yeah. So I might like add up the 0.1s to get to the 0.4. So I can think of it that way. And that's kind of the beginning, the first way. But then we want to help students make the transition to be thinking about it as 4 times 17 and then scale times 0.1 or a tenth.
Mm-hmm.
So do the 4 times 17 first and then scale it down. Now we actually deal with the bigger numbers first and then the smaller numbers.
And I think that's, can I jump in for a second?
Yeah.
So if the kids are used to this idea of scaling up times 10, thinking about the 4 times 17 and then scaling up to get 40 times 17, and they make sense of decimal place value and decimal relationships, then scaling down by 10 or scaling a tenth isn't as far reaching as maybe it feels.
It might sound.
When we're using some other.
And one other way I might put that is if we've got students that are we've done a lot of whole number work so that they are doing that 4 times 17 and then multiplying by 10, and they're used to watching those numbers shift in place value where that 0 comes in. Then now to divide by 10 and having those numbers shift the other way in place value is not a far reach. We want to make sense of it, but it's not quite maybe as crazy as it might sound. You're like, Pam, kids just move the decimal. Or not, or they're actually thinking about the values.
So that actually sounds like what I do when I'm thinking about a problem. Not always, depending on the numbers of the problem. But if you were to give me, say, a decimal times a decimal,
Mhm.
I'm very often going to like think outside the decimals, pull it back into what strategy do I want to use for whole numbers. And then I think about, okay, I have some version of the answer, some place value shift of the answer. And then I'll consider scaling down by 10, kind of reevaluating. Does that make sense? Scaling down by 10, seeing if that makes sense. And so I know that it sounds, or it could sound to some people that, oh, it's just exactly what we tell kids to do in the algorithm. Do the steps and then move it, move it, move it. But it's not it's
We
not
we can
like
make a
that in
rhyme
my
of that.
head, right?
Do the
Do it.
steps and move it, move it, move it.
Oh gosh.
No, no, don't do that. Don't do that. Sorry, I
But
interrupted you. So what?
I do stop along the way. Like with each shift, I stop and I say, is where I'm at in this moment, does it make sense for the numbers that then are in the problem? When I
And I would
shift again, yeah.
keep going, keep going, keep
I was
going.
going to say
Sorry.
for each shift, I stop, I reevaluate, I consider if it makes sense for the problem. Um, and so it's not this mindless like move over three places because the decimal has moved over three places in the problem or whatever.
It's much more thinking about the values
Yeah.
involved.
Yeah.
And so I'm going to suggest that my mom is from Switzerland. I say that just to say she grew up with the metric system.
Hmm.
And when I can get her to talk to me about what's going on in her head as she does math, I began to realize that she does what you do in that when she scales. So just like if whole numbers, if you were multiplying, like we were talking about before, if I was going to do something like 40 times 17, she would think about 4 times 17. And then
Uh-huh.
she would think about, okay, so 4 times 17 is this number. Then 40 times 17
Yes.
is, I'm going to multiply by 10.
Yes.
But if she was doing 400, so hang on, that's 680. I had to think about that for a second. So if 4 times 17 is 68, then
Uh-huh.
40 times 17 would be 680. But if she was
Hmm.
doing 400 times 17, Kim, this is what I find interesting, is she would not then say, oh, 2, like I know 4 times 17 is 68, but I'm doing 400 times 17, so move it, move it. She wouldn't say, oh, then I'm going to move the decimal point twice because from 4 to 400 is 2 decimal places. She would literally say, 4 to 40, so that's 68 to 680. And
Hmm.
then 440 to 400, that's 680 to 6,800. So
It's
she
one
kind of
step at a
does it
time. One
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 shift
one
at a time.
one shift at a time, one times
Hmm.
10, one power of 10 at a time. And I
Yeah.
said, what? And she's like, like if I'm going from centimeters to kilometers, I go
Mm.
from centimeters to meters and meters to kilometers. And
Right.
I was like, oh, that makes sense.
Yeah.
She had made sense of the relationships. And so then she was able to bring that into multiplication.
Hmm.
So, Kim, I'm going to give you an example. And I want you to, if you don't mind, we share with everybody how you're thinking about a problem
Sure.
like point 0.6 times 15.
That's 6
If I
times
said
15.
point 0.6 times 15, can you just tell us what's
Okay.
going on in your head?
Yeah, sure. So I would think about 6 times 15.
Okay.
And there are a variety of ways that I could do that. I actually happen to know 6 times 15 is 90. So
Okay.
because 6 times 15 is 90, then zero point 0.6 times 15 is going to be a tenth of 90. So it's one shift, one divided by 10. So instead of 90, it's going to be 9.
Which ends up being 90 divided by 10.
Right.
And so that's 9. And that's like, yeah,
Yeah.
nice. Nice. Kim, what if it had been 0.06 times 15?
It's funny because I think I would probably take the in between step, just like your mom talked about.
Uh-huh.
I would have said, I know 6 times 15 is 90. So zero point 0.6 would be 9. So 0.06 would be 0.9.
Bam. And that thinking, that sort of stopping and making sense, like, does that, yep, and then doing
Mm-hmm.
the
Mm-hmm.
next place value shift, yep, that's what we want to encourage in students.
Yeah, I think all too often we go, just count how many decimals there are, and then just go over to your answer and count how many decimals there are. And kids have no concept of is 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 it reasonable at all?
Yeah, magnitude and size and what it means to multiply by a tenth, and then what it means to use that to think and reason. So if y'all, it starts with whole numbers. It starts with
Mhm.
whole numbers and scaling up by multiplying by 10. And now that
Mhm.
we're dealing with decimals, we're dividing by 10. We can divide by 10 and make sense of the magnitudes in the problem. What's actually happening with the sense of size and scale. It's not about just do the whole number algorithm and then just move the decimal butt cheek. No. It is really reasoning. When we complain, oh my gosh, that answer wasn't even reasonable. Well, I would suggest it's because we took kids out of reasoning land to begin with. So we can help students make that same shift that we want to make in whole number multiplication. And we can do that with decimal multiplication as well. Kim, I am remembering that I was listening to us very carefully in this podcast, that we always said things like a tenth of or
I was
divided by
just
10.
about to say something like that. Yeah. Um, I don't know if I've told you this, but I have not always been as careful with my language. With in regard to a tenth of, or I have to really caution myself. But one thing I will never say is 10 times less. And I have to tell you, I was watching, I don't remember what show it was, but I was watching a show.
To mean what? To mean what though? You won't say 10 times less, to mean a
a
tenth
tenth
of.
of. Yes.
Yeah. So
Yes.
divided by 10 or a tenth of, we cannot say 10 times less.
Pam, I was watching a show the other day and there was a commercial, and in big, like bold letters across the screen, it was like 10 times less. And I was like, no, don't say that.
I'm trying to think.
I don't know what it was.
Which would be the worst? What's the better deal? Like you should go up to him and say, I want your deal. Or is that?
No.
Yeah. Anyway, so the language can be important, that we're looking at a tenth of, or we're taking that number divided by 10. We're not subtracting off when we're thinking multiplicatively about relationships. Yes. Is that a way to say that?
Yeah.
All right, cool.
Yeah. So listen, it's important for kids to make sense of what's happening first, and then we're going to get them more sophisticated, right? And then they're going to be super flexible and they can solve the problem in a way that makes the most sense to them. So next week, we're going to tackle some gnarly problems and share some of the flexibility that's happening in our heads.
So stay tuned. It's going to be fantastic. And thank you for tuning in and teaching more and more real math. To find out about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.